Good evening, everyone. Welcome to lecture 4 for the course Classics in Total Synthesis taken by Professor Krishna P. Kaliyappan. So, this is the fourth tutorial. We will wait for 5 more minutes to see whether someone is joining or not, and then we will start the session. Maybe by that time we can discuss last week's contents once again. So, I will share my screen. I hope my screen is visible. So, in the last week, we started with the discussion on the week one assignment, which due date was over last week. So, after discussing the week one assignment, we moved to the discussion regarding the week three lecture. Okay, thank you. So, we discussed about week three lectures and we started the discussion about triquinates and we saw the total synthesis of isocommine and then sulfifurfol, then heurostein and capnylane, which are linear triquinates. Then we saw some rearrangement, Wagner-Mervin rearrangement, Claisen rearrangement, their mechanisms, and we also discussed some questions regarding those topics. So that was the content for last week's session. So today also I have planned to do it in the same manner. That first we will be discussing the week two assignment, and after that we will be discussing the week four lectures. A brief summary of the all five lectures of week four. That was about triquinates. Then we will discuss some reactions which sir mentioned during those lectures, their mechanisms and some examples for that reactions. And then we will discuss some questions regarding that lectures. So that's how I plan today's session. We will wait for a couple of minutes and then we will start discussion on this week 2 assignment. So we may start our discussion on week 2 assignment. So the first question was, what is the correct sequence of steps followed to get the product obtained in the reactions given below? So this is the reaction between cyclopentadiene and a benzoquinone. So in a couple of steps it is shown to give this compound which is given here. This compound. So what is the correct sequence? So option A is photochemical followed by a photochemical reaction and thermal reaction. Then option B is 4 plus 2 cycloaddition followed by 2 plus 2 cycloaddition and FVP. Then 2 plus 2 cycloaddition followed by 4 plus 2 cycloaddition and FVP. Then 4 plus 2 cycloaddition followed by FVP and 2 plus 2 cycloaddition. So which will be the correct sequence to get this compound from the cyclopentadiene and benzoquinone? So this, I think, we have already discussed about this reaction in the four-member construction of four-member ring system in cubanes, as well as we saw this in the last week lecture series also in thermal metathesis. In that case also we saw the same reaction. So I hope this is familiar. So I will give you some time to think about this and what will be the exact sequence of steps. I hope everyone got the answer for this question. So the correct answer is 4 plus 2 cycloaddition followed by 2 plus 2 cycloaddition and FVP. So what is happening here is this cyclopentadiene serves as the diene for the Diels-Alder reaction. That is, first step is 4 plus 2 cycloaddition, and here in benzoquinone this one double bond will serve as the dienophile for the cycloaddition reaction, and it will undergo 4 plus 2 cycloaddition reaction. Then, as a result of that 4 plus 2 cycloaddition reaction, we know that a cyclohexene ring will be formed. So, in that cyclohexene, one bond is present, one double bond will be present, and already one double bond is present in the system. So, in the second step, that two double bonds will undergo a 2 plus 2 cycloaddition reaction, and it will result in the formation of Cooksen's dione. I hope you remember the structure which we already discussed in our previous classes also. So first this 4 plus 2 cycloaddition followed by this 2 plus 2 cycloaddition will give us this Cooksen's dione. Then on heating it can undergo pyrolysis, that is FVP, and it can undergo pyrolysis, and it will like a retro 2 plus 2 type of reaction will take place, and this will be forming. So first 4 plus 2 cycloaddition, then that two double bonds will be there, that will undergo 2 plus 2 cycloaddition followed by FVP. I think I have the structure for that Cooksen's dione. I will see once. Yes, so this is the Cooksen's dione. So first the cyclopentadiene and this benzoquinone will give this 4 plus 2 product, which upon 2 plus 2 cycloaddition will give this compound 4, that is Cooksen's dione, and when it undergoes a retro 2 plus 2 condition upon pyrolysis, we will get that product which is given in the question. So that was the first question from assignment 2, week 2 assignment. Now this is the second question. The correct match for the structures of prostaglandins in column 1 with their names in column 2 is. So here we should have a better understanding about how the nomenclature of prostaglandins are done. So I will give some time. So you have to match the correct answer, like which prostaglandin is having this particular name: PGA, PGC, PGE, PGF. So I will recollect that nomenclature for prostaglandins once again. So prostaglandins, we know they are carbocyclic oxygenated C20 molecule. So their classification is based on the nature of functionalities present as well as the number of unsaturation in the two side chains. So PG in this nomenclature, this PG stands for prostaglandins. Then in the case of PGA and PGB and PGC, all are having cyclopentanone, but there is difference in the position of double bond. So in the case of PGA and PGC as well as PGB, which is not given here, it is having cyclopentanone ring in common, but the position of the double bond differs in the case of PGA, PGB, and PGC. So, from these options, we can conclude that this PGA and PGC is either the C or this D, because both are having cyclopentanone, only the position of double bond is different. Now, in the case of PGD and PGE, there is no double bond, but a ketone and hydroxyl group is there. So there is only one such option. Therefore, PGE will be this option B, because there it has this ketone and hydroxyl group. So PGE and PGD is having no double bond but ketone and beta hydroxyl group. Now moving to the PGF, it is having hydroxy group, both the two hydroxy group in the cyclopentane ring. So option 4 will be matching with option A. So which will be the correct answer? Option A 4 and B 3, we have two options, A and C. So we have to understand whether PGA is C or PGA is D or PGC is C or D. So for that, PGA is having a structure which is having this unsaturated alpha beta unsaturated ketone without substitution. So PGA corresponds to this structure C and PGC corresponds to the structure D. So answer is option A. So this is PGF, this is PGE, this is PGA, and this is PGC. So PGA, PGB, and PGC is having cyclopentanone, but the double bond position is changing. So this will be PGA. If double bond is here, it will be PGB. If double bond is here, it will be PGC. Then in the case of PGE and PGD, there is no double bond, but a beta hydroxy ketone is present. So this is the structure of PGE. Then in the case of PGF, there is no ketone, both will be hydroxyl group. So I hope it is clear. Now moving to the third question, identify the correct transformation taking place in the reaction given below. This also we have discussed in the last class, what is conrotation, what is disrotation, what is the difference between 6 pi electrocyclization, what is the difference between 8 pi electrocyclization. So what is happening here and which is the transformation? Conrotatory 6 pi electrocyclization, disrotatory 8 pi electrocyclization, conrotatory 8 pi electrocyclization, disrotatory 6 pi electrocyclization. This also we discussed in during our discussion on cubanes. We saw this type of electrocyclization reactions. So here as we can see, this 4 double bonds are involved in the cyclization reaction. So it is actually an 8 pi system. So the electrocyclization is 8 pi electrocyclization rather than 6 pi electrocyclization. Because we can see here and 1, 2, 3, 4, 5, 6, 7, 8 membered ring is forming. And what is happening here is this is shifting to here and This is shifting to here, this to here. Sorry for my poor drawing. And this to here. So it will result in the closing, and it will give us this. Now about the stereochemistry, whether it is rotating in the same direction, these groups, or not these groups, actually this lobes, whether it is rotating in the same direction or it is rotating in the opposite direction. So as we can see, this both the groups are rotating in the opposite this or both the groups are present opposite. Like this is alpha and this is beta. So here the rotation is like to same side. This is rotating to this side and this is rotating to this side. Then only we can get this product. So this kind of rotation is known as con rotation. So here the answer is con rotatory 8 pi electrocyclization. These four double bonds are involved in the cyclization, so it is an 8 pi system and we are getting an 8 member ring. And in the case of disrotation and conrotation, both these orbitals are rotating in the same direction, so that we are getting this corresponding stereochemistry. So the answer is conrotatory 8 pi electrocyclization. So our next question is, identify the correct order of reagents used in the following transformation. So here as we can see, the only reaction what has taken place here is this OH being protected with this TPDPS group. So for that, the given options are simple protection of TBDPSCl, imidazole, DCM 0 degrees Celsius. Then first step iodine and K2CO3. Then second step is TBDPSCl and base. Third step is zinc dust and acetic acid. Then C, TBDPSCl, N-butyl lithium and minus 78 degrees Celsius. Then option D is first step zinc dust acetic acid, second step TBDPSCl base, and third step is iodine and K2CO3. So which will be the correct order of reagents used in this particular transformation? So this was during the discussion of endandric acid, we saw the series of reaction. So here, as I told you, their aim was to just protect this hydroxyl group using TPDPS. So first they tried this condition, TPDPS-Cl, imidazole, DCM at 0 degrees Celsius, but what they were facing was the selectivity. So in that case, both this hydroxyl group were getting protected. So they gave up that attempt and they tried different condition. So other than this TBDPSCl, direct protection of this hydroxyl group, which will be the condition they would have tried to increase the selectivity of the reaction, so that they can protect only that primary hydroxyl group. Both are primary, that's why they were facing the selectivity issue. They wanted to protect this hydroxyl group a lot. So here what they did was to improve the selectivity of this reaction. They first treated this compound with iodine and K2CO3. In that case, what happened was a famous reaction which is known as iodolactonization takes place. So, since this alkene is adjacent to this hydroxyl group spatially, so here first by treating with iodine, this iodine came here and this double bond will not be there, and here this iodolactonization iodine like this kind of reaction takes place, and in that this lone pair in this oxygen went and attack, and this was opened, so iodine came here with the formation of a lacton ring. So I hope it is clear. So here this iodonium ion will be forming, and in that this oxygen will be attacking here, and that iodonium ion will open, ring will open, and here iodine will come and oxygen will be bonded to here. Then there is no free hydroxyl group to hamper the protection of the this hydroxyl group using TBDPS Cl. So what they did in second step, they protected this hydroxyl group using TBDPS Cl and base. Then what they needed was the opening of this lactone and formation of this double bond and removal of this iodine. Because here in this position, iodolactonization took place previously by treating with iodine in K2CO3 condition. And for the removal, they use zinc dust and acetic acid condition, and they got this back. Zinc dust and acetic acid is known to open this kind of lactone ring. So here the correct sequence is iodine in K2CO3 for iodolactonization, then the protection of the hydroxyl group selectively using TBDPSCl and base, then opening of the lactone formed, opening of the ring formed and giving the desired product by using zinc dust and acetic acid. I hope it's clear. We will move to the next question. The major product formed in the following reaction is. So here a diazo compound, ketone is given, and which will be the major product formed in the following reaction. This I think we discussed in the beginning of prostaglandins, where not prostaglandins, in the four-membered rings where beta lactams are required. In the case of penicillin, we discussed this kind of reactions. So, what will be the product under photochemical condition if we are treating this diisoketone? What will be the product? And this reaction is going through the formation of a particular kind of intermediate, which is that intermediate. So here, under photochemical condition, this from this diazo compound, the stable nitrogen molecule will be eliminated, and here carbene will form, and that carbene can attack this position. So it will be 1, 2, 3, 4. It will result in the formation of a beta lactam ring. So the correct answer is option A. This we discussed while discussing various methods to construct the beta lactams in penicillin, and one such reaction was this carbene insertion reaction. So here carbene is not isolated. We are treating this compound directly under photochemical condition, and we are getting this beta lactam ring. So that means in situ carbene is forming, and through that carbene intermediate this reaction is proceeding. Correct answer is option A. Now moving to the next question. Identify A in the following reactions. So this also we discussed during our discussions on cubanes. So which will be the corresponding starting material to get this cubane, this carboxylic acid. So here the reaction is Favorsky rearrangement, which we already discussed, I think, in last tutorial, and the last to last tutorial also we discussed that reaction in detail. So for the formation of this cubane carboxylic acid derivatives, we are using corresponding this haloketones. For the formation of this four membered ring, we will be taking the cyclopentanone as the starting material, and there it will be undergoing Favorsky rearrangement to get the corresponding product. And I have also told that to get this carboxylic acid, the starting material should have this carboxylic at the should have a halogen at the position of this carboxyl group. So the correct answer will be option C. So just we have to replace in the starting material. What we have to do is we have to replace that particular four membered ring with the cyclopentanone, and that carboxylic acid should be replaced with the halogen. So that is Favorsky rearrangement. I will show that mechanism once again. If needed, you can go through that. See, as we can see, this is the example given in that question also. This corresponding starting material giving this product. So the mechanism of Favorsky rearrangement is like that. This we are using KOH. That KOH will be abstracting this alpha proton, and here it will generate a carbanion which will attack the alpha position to that halogen, and our halogen will be eliminated to get this kind of intermediate. Then again that OH minus will be attacking at this carbonyl carbon center, forming this kind of compound, and then when this O minus will come back as ketone, this three membered ring will open, resulting in the formation of this five membered ring. So it is like a ring contraction reaction. Here from the six membered ring, we are getting five membered ring as the product. So if we are taking five membered ring as the starting material, we will be getting four membered ring as the product. So it is a kind of ring contraction reaction, that is Favorsky rearrangement. So option C is the correct answer in this case. Note here, option C is the correct answer. Then moving to the next question. Identify the reaction taking place in the reaction given below. So this is also another electrocyclization. So what is happening here? Conrotatory 6 pi electrocyclization, disrotatory 8 pi electrocyclization, conrotatory 8 pi electrocyclization, disrotatory 6 pi electrocyclization. So the same example we discussed in one of our class also. I think last class also we discussed about this example. So here actually we can see from this 8-membered ring we are getting a 6-membered ring and a 4-membered ring. So what will be happening here? This is actually a 6 pi electrocyclization. So one of the bond is not participating in the reaction, and this bond might be shifting here, and this will be shifting here, resulting in the formation of a 6-membered ring and a 4-membered ring. So this is like, this will form a 4-membered ring here, and this will mm, one, two, yes, this will form the 6-membered ring. And so it is a 6 pi electrocyclization. And what will be the transformation, conrotatory or disrotatory? So here as we can see, here both are having opposite stereochemistry, but in the product, as we can see in this 4-membered ring, this group and this hydrogen, that is hydrogen over here, is oriented in the same direction. So here the rotation will be like this to here and this to here. So the rotation will be like in opposite direction, then only we can get this corresponding product. So it is disrotatory 6 pi electrocyclization. I will show that example which we discussed earlier. Yes, here we have seen such a similar example. So here we are getting from this starting material this 8 pi conrotatory, we are getting this product, and there it will be undergoing a 6 pi disrotatory. So it will be like this, three double bonds are involved, and it is 6 pi disrotatory, and we are getting the 6-membered ring fused with this 4-membered ring. So the similar is happening in this case also. So here also there are 6 pi electron systems. So this will be shifted to here, this will shift to here, and this will move to here. So it will form one 6-membered ring and one 4-membered ring. So here stereochemistry is already fixed. So corresponding to that, it will be disrotatory 6 pi electrocyclization. Now moving to the next question, identify the major products A and B in the following reaction. First, this lactone is treated with NaOH and H2O to give A. Then it is treated with Ki and sodium bicarbonate in presence of H2O to get the B. So which will be the corresponding A and B in the following reaction? Identify the major products A and B in the following reaction. So here what is happening? First is the hydrolysis of this ester bond. So here it will be cleaving and we will get NOH, and corresponding here it will be forming here OH, and here corresponding acid we will get. So which will be the corresponding A. There are, I hope you can see, as you can see, all the corresponding A is like that only. The hydrolysis of this ester to give OH here and this COH here to get the 5-membered ring. So A is fixed, but actually the problem is the stereochemistry. So as we can see, this OH and this group is having the opposite stereochemistry in the starting material. So in the product also it will be having opposite stereochemistry. So but in the case of option B and option C, the A is A in A, we can see this OH and this group is having same stereochemistry which is not matching with that of the starting material. So we can discard this two option B and option C. Then the next reaction will be Ki, NaHCO3 and H2O. So in that case, here iodolactonization is taking place. That is, here iodine will be forming this iodonium ion, and that will be in the opposite direction of that of the uh, yes, iodonium ion will form, and on that iodonium ion, this hydroxyl group will be attacking, and that attack will be directed by this hydroxyl group. So that attack will be from the same side of the hydroxyl group, and therefore the correct answer will be option D. Option D will be the correct answer. So first step is this ester hydrolysis to give alcohol here and this carboxylic acid here, which will be having the same stereochemistry, but corresponding to this it will be having opposite stereochemistry. Then iodolactonization will give the corresponding product B. So option D is the correct answer in this case. Now moving to the next question, identify A in the following reaction. So this is another method for the construction of beta lactams by using PCl3. So which will be the starting material here in this case. So here we have already discussed that in the formation of beta lactams, first reaction we discussed was cyclization reaction. So for cyclization reaction, we told that in the case of beta amino acids in presence of certain reagents, including acyl chloride, phosphorus trichloride, and thionyl chloride, so this beta lactam formation will be taking place. So here the correct answer is this option C. Actually, this option C and option D are same. So here first step is like acylation and then followed by nucleophilic attack on this nitrogen. So for that one hydrogen, one proton only should be available. Otherwise, it can undergo both of this can undergo reaction. Both these protons are reactive. So this one mono substituted nitrogen should be there. So we can say this is the correct answer for the formation of beta lactam using PCl3. Now moving to the last question of this assignment. So identify the major product A in the following reaction. So obviously there is a diene and a dienophile. So this is Diels-Alder reaction, and just you have to see what will be the stereochemistry and which product will be the major product. So here as we can see, this diene and this dienophile will react to give endo as the major product due to secondary orbital interaction since this ester is present in this dienophile. So as a result, we know this TBDPS group and this group and the CO2Me will be having opposite stereochemistry. So I think we have two such options, and what is the difference between these two options? This stereochemistry of this group. So as we know, it will be like this will be like it will be like and CO2Me will be towards this side. So this group and our CO2Me will be having the same configuration, same stereochemistry, and the CO2Me and TBDPS, or this methyl group and this TBDPS will be having opposite stereochemistry. So which will be the correct answer then? Option A will be the correct answer. As a result of Diels-Alder reaction, we will be getting this product with this endo product as this major with this stereochemistry as mentioned in this product. So that was about the week 2 assignment, 10 questions. I will give you some time to go through all the questions. This was the first question, the correct sequence of steps followed to get the product obtained in the reaction given below. And the correct sequence was 4 plus 2 cycloaddition followed by 2 plus 2 cycloaddition and then followed by pyrolysis, thermal pyrolysis, that is FVP. Then the correct match for the structures of prostaglandin in column 1 with their names in column 2 is. This also we discussed in detail. Correct answer is option A. That is first one correspond to PGF, second one correspond to PGE, third one correspond to PGA, and fourth one corresponds to PGC. Now the third question was the correct transformation taking place in the reaction given here. Conrotatory 6 pi electrocyclization, disrotatory 8 pi electrocyclization, conrotatory 8 pi electrocyclization, or disrotatory 6 pi electrocyclization. And conrotation means it is both the orbitals are rotating in the same direction, that is either clockwise or either anti-clockwise. Disrotation means one orbital will be rotating in clockwise direction, other orbital will be rotating in opposite direction, that is anti-clockwise direction. So here also we saw the correct answer is conrotatory 8 pi electrocyclization. And our next question was the correct order of reagents used in the following transformation for the protection of that selective protection of hydroxyl group. One of the hydroxyl group using TBDPS. So here, due to the selectivity issue, first was hydrolactonization, then protection, and then using zinc dust and acetic acid, opening of that lactone ring and removal of iodine. So this is the correct answer, option B. Then the next question was this, the major product formed in the following reaction. Diisoketone upon photochemical condition, what will be the product with the starting material? So here as we have seen, it is going through the carbene formation. First, by the elimination of this nitrogen molecule, carbene will be formed here and it undergo carbene insertion up on this carbon, which will result in the formation of a beta-lactam ring. So option A is the correct answer in this case. Now the next question was the identify A in the following reaction. Starting material, this is a Favorsky rearrangement, so which will be the corresponding starting material for this reaction. So obviously it should be an alpha haloketone. There is only one alpha haloketone given in the options. That will give the corresponding carboxylic acid with the 4-membered ring from this 5-membered ring. And option C is the correct answer in this case. Then the next question was identify the reaction taking place in the given reaction given below. So here from this 8-membered ring, we are getting one 6-membered ring, that is a diene, and a 4-membered ring with corresponding substitutions. So what will be the correct transformation, conrotatory or disrotatory, and what will be the uh, reaction, 6 pi electrocyclization or 8 pi electrocyclization? So here the correct answer is it is a 6 pi electrocyclization. 6 pi electrons are involved and the rotation is disrotatory 6 pi electrocyclization. The next question was identify the major products A and B in the following reaction. First, hydrolysis of ester followed by iodolactonization and opening of that uh, iodonium ion formed with the help of that carboxylic acid hydroxyl group. So, which will be the correct answer and corresponding stereochemistry. So here the correct answer was option D, that is first this corresponding ester hydrolysis product and then the cyclized product will be forming. With this carboxylic acid and alcohol having the same stereochemistry and this group having the opposite stereochemistry. Next question was identify A in the following reaction. So treatment of compound A with PCl3 is giving beta-lactam ring. So which will be the corresponding starting material. So here this is the correct answer. It is like this NH proton will be reacting first followed by the cyclization to give the corresponding beta-lactam ring. And the last question was identify the major product A in the following reaction. So it is a Diels-Alder reaction. So which product will be major with the correct stereochemistry? So option A is the correct answer. That is the endo product with the corresponding stereochemistry. So now maybe we can move to the discussions on the week 4 lectures. So 5 lectures was there. All lectures was about triquinanes. So in the first lecture we saw the triquinane synthesis by radical cyclization as the key step, where we saw the total synthesis of sulfipherfolene and modifine by Karen's group. And sulfipherfolene, as the structure is shown here, it is an angular triquinane, and modifine, which we will see, that is a propylene type triquinane. And so this lecture is basically involving um, only the repositioning of a side chain on the cyclization template to get this angular triquinane by the extension of tandem radical cyclization strategy. So key reaction was this 5 exotrophic radical cyclization, and the starting material used was 3-ethoxy 2-cyclopentenone. And one of the reaction which is involved here is one named reaction which we came through was Wolff-Kishner reduction. So this total synthesis was completed by Karen in 1987 in 7 steps with a 6.4 percentage of overall yield. So the key step was radical cyclization, which is 5 exoteric radical cyclization. Now another natural product which we discussed in this lecture was, modifine, which is a propylene type triquinane. Another example was polychiral, and we saw many other examples for this propylene type triquinane. So this modifine was first isolated from goldenrod plant, and it is known for its toxicity towards cattle and sheep, and it is having a 333 propylene type carbon framework. And the Karen was the first to report the total synthesis of this modifine in 1990, and the principal problems in this total synthesis were the presence of these three contiguous stereo centers, as we can see, one, two, three contiguous stereo center. Then the control of relative stereochemistry at the stereo center having this methyl group. Then this architecture of this propylene type structure does not permit a tandem radical cyclization, but it should be done in like a stepwise radical cyclization manner. So this was the principal problems in that total synthesis. And here, current synthesis use cyclopentene 1,3-dione as the starting material. And the key steps were Ireland Claisen rearrangement, radical cyclization, Negishi coupling, and he could obtain this modifine in 14 steps in 18% with 18 percentage of overall yield. So the principal problems were three contiguous quaternary centers, control of relative stereochemistry at the stereo center bearing this methyl group, and this architecture of this propylene ring system does not permit this tandem radical cyclization, but it should be done in a stepwise manner. And this synthesis is one of the main peculiarity of the synthesis was it demonstrated the utility of fragmentation method for achieving high yield and high stereoselective on an intramolecular 5XO cyclization. So we saw several named reactions in this synthesis. First was Wolff-Kishner reduction for this Hilfiferfol, and then we saw this Ireland-Clayson rearrangement and Egishi coupling in the case of Modifine. So we will discuss the mechanism of these named reactions. So this is Wolff-Kishner reduction, that is ketone is converted into corresponding alkane by using hydrazine and water and this KOH as base. So this is Wolff-Kishner reduction, ketone to corresponding alkane. So the mechanism is that first with the treatment of this hydrazine, it will form this hydrazone, and this from this hydrazone, this OH minus from this KOH will be abstracting a proton, resulting in the formation of this compound. And this intermediate, when this negative charge comes over here, this will comes over here, and that will get quenched with one proton to get this product. And again another OH minus can abstract next proton from this hydrogen, where the carbanion moves to here, and this here will create another negative charge which will be quenched with another proton. So this ketone will be converted by two proton source into this, from water into this corresponding alkene, and here the byproduct will be this nitrogen from this hydrazine. So this is the mechanism of Wolff-Kishner reduction, conversion of ketone into corresponding alkane by using hydrazine and base. So first hydrazone formation, then abstraction of proton from that hydrazone nitrogen, then quenching of that carbonyl carbon, that corresponding carbon with proton, then again abstraction of proton by the hydroxyl group, and again quenching of that minus charge with proton. So that was the discussion about Wolff-Kishner reduction. Then the next was Ireland-Clayson rearrangement. So it is like first enol TMS formation by using a base, then it is undergoing rearrangement. So it is a 3,3 sigma tropic rearrangement. We will see the mechanism of this rearrangement. So using LDA, it will abstract this proton, and this will create the enolate, which will be quenched by this TMSCl. So it will result in the formation of this compound. Then it is like a system which can undergo this 3,3 sigma tropic rearrangement. So it will be like 1, 2, 3, 1, 2, 3. So 3,3 bond will be forming, 1,1 bond will be breaking, and this bond shift to here, this bond shift to here, resulting in the formation of ketone here, and this will come here. Then upon hydrolysis, this silyl ether group will be converted into corresponding alcohol. So that is the mechanism of Ireland-Clayson rearrangement. First, this ketone will get enolized by using LDA, and enolate will be quenched by TMSCl. Then it will undergo 3,3 sigma tropic rearrangement, followed by the removal of that silyl group by using NaOH and water. So this is known as Ireland-Clayson rearrangement. Next was Negishi cross-coupling reaction, which is a palladium catalyzed cross-coupling between this zinc halide compounds and this other like alkynes coupled with the zinc, and then this type of halides, which will result in this coupling between R1 and R2, resulting in this carbon-carbon bond formation through the zinc complex, and it is catalyzed by palladium or nickel. So this is known as Negishi cross-coupling reaction. So these are the examples. So here this carbon and this carbon will form bond. Here this carbon and this carbon will be forming bonds under palladium catalyzed condition. So this is known as Negishi cross-coupling reaction. So here the mechanism is first the oxidative addition of this halide into this palladium, giving this complex. Then our alkyne zinc complex will be inserted into this, undergoing transmethylation. By the elimination of zinc halide, we will be getting this compound. Then cis trans isomerism, because for reductive elimination to take place, the eliminating group should be in cis position. So it will come in cis position, and then reductive elimination will give our corresponding product. So this mechanism is like in general for every coupling reactions, it will be oxidative addition, transmethylation, and reductive elimination. Here also it is same. So that was the discussion about lecture 16, that is trichonanes by radical cyclization, where we saw the total synthesis of this sulfipherol and this modifine using 5-exotrig radical cyclization as the key step by Karen's group, and this mechanism of Wolff-Kishner reduction, and this Ireland Clayton rearrangement, and Negishi cross-coupling reaction. And the next lecture was about trichonanes by photochemical reaction. So here what we have seen is the application of oxidipymethane rearrangement and photochemical 1,3 acyl shift in the total synthesis of sulfipherol and capnylate by Demuth and Uehara group. So the key reaction was oxidipymethane rearrangement in this case by photochemical reaction. So first we saw the total synthesis of sulfipherol by Demuth's group in 1988. So here a tricyclic enol which was required was obtained from the chiral enol via Diels-Alder methodology, and the key reaction was oxidipymethane rearrangement, and the starting material was Hages-Parrish ketone which could be prepared from the methyl vinyl ketone and 2-methyl 1,3 cyclopentadiene. Then it took 11 linear steps and 1.6 percentage of overall yield. He could complete the total synthesis of this natural product. So this is the formation of this Hages-Parrish ketone. That is, it is actually a Robinson annihilation reaction taking place followed after this Michael addition product. So here 2-methyl cyclopentene 1,3 dione and methyl vinyl ketone. This will undergo addition at this position, that is Michael addition at this position, and it will give this compound. Then this compound upon treatment with this esprolin, it will give the cyclized Robinson unrelated product with this corresponding stereochemistry, which upon treatment with this paratoluene sulfonic acid, we will get the dehydration and we will get this double bond corresponding to this position. So this is the structure of Hages-Parrish ketone, which was the starting material for the synthesis of this sulfipherol 16,5-1. And here the mechanism of this Robinson annihilation is like that. After this compound form, this S-prolin will get bonded with this corresponding. Yes, this S-prolin will be bonded with this corresponding ketone present in this here with a hydrogen bond, and that will direct this Robinson annihilation. It will abstract this proton, and that can, like, it is like it can abstract this proton and it will attack at this, it will attack at this position, and then corresponding to that here hydroxyl group will be formed, and then dehydration will give this corresponding Hages-Parrish ketone. So this is a carboxylic acid catalyzed enamine mechanism. Different mechanisms are possible, and here they have given this amino acid S-prolin catalyzed carboxylic acid catalyzed enamine mechanism. So here corresponding to this first enamine will be forming like this enamine formation will take place, and then cyclization will give this compound followed by the dehydration will give us the Hages-Parrish ketone. Then the next reaction which we mentioned was oxidipymethane rearrangement. So it is also a photochemical reaction. So as we can see here, in the case of, in the present, in the place of an alkene, we are getting a cyclopropane ring, And the mechanism is like that: upon photochemical condition, here this bond will undergo homolysis, and this bond will undergo homolysis. So here will be one radical, here will be one radical, here one radical, and here one radical. So these two radicals will combine, resulting in the formation of a cyclopropane ring, and this radical will go back as ketone, and then after that this bond will be cleaving, resulting in one radical over here and one radical over here. So that will give this corresponding compound, oxidipymethane rearrangement. Another possibility is that after breaking of this bond, this two will be combining to give the corresponding alkene here, and then this two will be combining to give this corresponding epoxide ring. So this is the mechanism for oxidipymethane rearrangement, which is a photochemical reaction to convert this corresponding alkenes into cyclopropane rings. This we have seen that if 1,3-acyl shift is taking place, cyclobutanone will result rather than cyclopropane. So this is two examples for this corresponding um, this oxidipymethane rearrangement. So here it is like this bond is getting reduced to 5-membered bond, and this is getting converted into a cyclopropane. Here also we have seen as before, it is giving the cyclopropane ring as a product. So this is the mechanism. This bond will be cleaving, this bond will also be cleaving, and this will give cyclopropane. And when this radical will go back to here, such that this bond is breaking, so here it will be double bond O. So here it will be one radical, and here it will be one radical, which will combine to give this cyclopropane ring. And this, as we mentioned earlier, is not that much favored reaction. Then we saw the discussion on this capnylane, which is having geminal dimethyl group, exocyclic methylene, and a tertiary methyl group by Euhera group in 1989, which was completed in 13 linear steps with 3.7 percentage of overall yield. And the starting material used was metacresol methyl ether. And the reactions which we mentioned here include Sujitro's reaction, Birch reduction, Diels-Alder reaction. So here actually a photochemical 1,3-acyl shift in a bicyclic system for generating this dicunene unit of capnylane. And here we are using ketene synthetic equivalent as alpha chloroacrylonitrile. And this Birch reduction and Diels-Alder reaction we already know, and we have seen it in the previous classes as well. So this is the Suji-Trost reaction, that is a palladium catalyzed allylation. Pi allyl complex will be forming from this, and then on that this nucleophile will be attacking. So this is the mechanism. So for this, on this palladium complex, first this it will coordinate to this double bond, resulting in this pi allyl complex by this elimination of this leaving group. Then onto this pi allyl complex, this nucleophile will be attacking, resulting in our desired product. So this is Suji-Trost allylation. So that was the discussion about the lecture 17, where we saw the total synthesis of sulfipyrrole and capnylane. Sulfipyrrole by Demons, where the key step was the oxidipymethane rearrangement, and the starting material was Hydrosparish ketone. In 11 linear step, he could complete the Demons group could complete it in with 1.6 percentage of overall. Then we saw the synthesis of Hydrosparish ketone and oxidipymethane rearrangement and its mechanism with some examples. Then we saw the total synthesis of capnylene, which is by Euhera group in 1989, with 13 linear steps with 3.7 percentage of overall yield, with metacresol methyl ether as the starting material, and the reaction involved are Suji-Trost reaction and Birch reduction and Diels-Alder reaction. And we saw the mechanism for the Suji-Trost reaction, which is through the formation of a pi-allyl palladium complex and catalyzed by palladium catalyst. So now moving to the next lecture, that is also tricunanes by photochemical reaction. So here in In this lecture, we have seen the total synthesis of various natural products, various trichonates, and in all that cases, the key step was the application of TMS iodide mediated rearrangement and arene olefin meta photocycloaddition. So first was the total synthesis of heuristin by Oda's group, where we saw the key step was the same TMS iodide mediator rearrangement, and he could achieve the total synthesis in four steps in 1986 with an overall yield of 36 percentage, and the starting material was cyclohextuene 1,4-dione. Then we saw the Oda's total synthesis of capnylene. And this capnylene was first isolated in 1978 by Gerasi from soft coral Caprella imbricata. And the key step for this synthesis was intramolecular titanium mediated ester ketone reductive coupling as the key reaction. And he could complete this in six steps, and one of the reaction involved was McMurray coupling. And here also the starting material was cyclohextuene 1,4-dione, which was obtained from this cyclopentadiene and benzoquinone by Diels-Alder reaction, and then reduction of the double bond followed by retro-Diels-Alder by pyrolysis. Then 2 plus 2 cycloaddition with butylene. So here also the key step was TMS iodide mediated rearrangement, and this first order synthesis of capnylene was achieved by the Sodas group in 1987, and another key step was the McMurray coupling, that is titanium mediated ester ketone reductive coupling, and he took six linear steps to complete the total synthesis with 25% of overall yield. So that was the Oda's total synthesis of capnylene. Then we saw the Vendor synthesis of isocomine, where we saw 2-bromotoluene, methylphenol ketone, and bromobutane was the starting material used, and arene photocycloaddition was the key step involved in that synthesis. Then we saw the total synthesis of this ceratopicanol by Cannon's group, where in that case also intramolecular arene olefin meta photocycloaddition as was the key step, and this was completed. Its starting material was an aldehyde, and this total synthesis was completed in 1996 in seven steps with 19.2 percentage of overall yield. Then the next total synthesis was by Vender's group for the supergorgic acid, which is an angular triquinane. And here also benzylic ketal assisted stereocontrol intramolecular arene olefin metaphotocycloaddition was the key step. And the starting material was 2-bromo 1,4-dimethyl benzene. And he could complete this total synthesis in 11 linear steps with 15% of overall yield. And this is the McMurray coupling, which we saw in that lecture, that is a titanium mediated coupling reaction between the ketones to give this alkene, and this mechanism is more clear in this. That is, first this homolysis of this ketone, and it will be coordinated with this titanium to get this, or either it will be cleaved to get this single product, where this titanium oxide will be eliminated to give the this radical, which can combine with the another radical to give this corresponding product alkene. So that was about the lecture 18. So we saw the total synthesis of heuristin, capnylene, isocomine, ceratopicanol, and the subarachnoic acid. And in all these cases, in the first three cases, we have this TMS iodide mediated thermal rearrangement was the key step. Then in the last two cases, we have seen arene photocycloaddition with an olefin was the key step in the case of ceratopicanol and subarachnoic acid. And for this capnylene, we have also seen this titanium mediated ester ketone reductive coupling is also involved, that is McMurray coupling. So we discussed about the mechanism of the McMurray coupling also, which is a titanium mediated cross coupling between ester or ketones to give the corresponding alkene. So that was about the lecture 18. Now moving to the lecture 19, which was the triquinanes by thermal metathesis. So here we have seen the synthesis of heuristin and another molecule called deoxymagnellanin and ceratopicanol. So here in this lecture, we have seen the application of photothermal metathesis reaction and intramolecular Michael addition in the total synthesis of histidine and deoxymagnellaninol by Mehta's group. So first for the synthesis of this tricyclic 6-q-terpene hydrocarbon, this plus or minus histidine involved a novel photothermal metathetic sequence as a key step to generate this linearly fused this tricyclopentanoid framework, which was done by Mehta's group in 1981. And the starting material was cyclopentadiene. And here we are discussing about the thermal metathesis that we already saw in the one of the example discussed today. So first will be 4 plus 2 cycloaddition reaction between cyclopentadiene and benzoquinone. Then 2 plus 2 cycloaddition between photochemical cycloaddition, which is intramolecular to get the Cooksen's dione, then which on pyrolysis undergo retro 2 plus 2 to get linear triconane core structure in 3 steps. So in 3 steps, Mehta's group could achieve the core structure of this linear triconane histidine, and the atom economy was 100 percentage. And so in total 12 linear steps, he could complete the total synthesis of this histidine with 13.1 percentage of overall yield. So first the 4 plus 2 cycloaddition between cyclopentadiene and benzoquinone, and then 2 plus 2 intramolecular 2 plus 2 photocycloaddition. Then to get the Cooksen's diene, which undergo upon pyrolysis, it will undergo retro 2 plus 2, get the corresponding core structure of this linear triquine. Then another molecule which we saw the total synthesis by Mehta's group was deoxymagnellaninol, which is not exactly triquinane. I didn't include the structure here. It is having a 2 5-membered ring and 1 6-membered ring and 1 N-methyl piperidine ring. It is having like a diquinane like of structure. And in that case also, thermal metathesis and intramolecular Michael addition was the main key reactions in the total synthesis. Then we saw that he is also using Walker process to get the methyl ketone. Then this synthesis was completed by Mehta's group in 1990 from cyclopentadiene and benzoquinone. He took 11 linear steps with 2.03 percentage of overall yield. Then the next molecule which we saw was ceratopicanol, which was isolated in 1988, and it is having this 5 contiguous 5 stereo centers, that is also in cis anti-cis fashion. So in 1991, Mehta's group reported the first enantioselective total synthesis in 14 steps, starting from R-limonene, which is the chiral pool for this total synthesis. And the key reactions involved are orthoester Claisen rearrangement and acid catalyzed disoketone olefin cyclization for creating these two quaternary carbon stereocenters. These two. Then another named reaction involved in the synthesis is Johnson-Claisen rearrangement, which will give gamma delta unsaturated carbonyl compounds. So this Johnson-Claisen rearrangement is known to give gamma delta unsaturated carbonyl compound, and this total synthesis he could complete in 14 linear steps with 0.9 percentage of overall yield. So this is the which we discussed, that is thermal metathesis, cyclopentadiene and this benzoquinone. It will give this product by 4 plus 2 cycloaddition reaction, which upon photochemical condition it will undergo 2 plus 2 cycloaddition reaction to get this Cooksen's diene, which upon pyrolysis 2 plus 2 retro 2 plus 2 will take place to give this product. So this is the core structure of this linear triquinanes, histidine and ceratopicanol, where he is using a thermal metathesis to get this core structure in 3 steps with 100 percentage of atom economy. So we discussed the total synthesis of histidine and ceratopicanol, and one reaction which we came through was this Walker oxidation and this Johnson-Claisen rearrangement. So Walker oxidation is basically the conversion of this Walker oxidation is the conversion of this alkene into corresponding methyl ketone. So it is catalyzed by palladium, and we are using this copper salt as the co-catalyst. So first step will be the generation of this PDCl2, and then again PDCl4, and which will undergo this coordination with this alkene to give this pi alkene complex, and then ligand exchange is taking place with this water, and one of this chlorine will be replaced with this water to get this compound. Then again onto this alkene, this water molecule will be attacking, so this pi allyl will convert into this kind of complex where this carbon will be directly coordinated to this palladium, and then elimination of one HCl molecule will result in OH here. So there a beta hydride elimination will take place again to form this kind of pi allyl complex, and then this pi allyl complex again undergo insertion reaction, and this reductive elimination we will get this methyl ketone as the product. So this is Walker oxidation, conversion of this alkene into methyl ketone. So it is like anti-Markovnikov's product. This is Walker process, Walker oxidation. So here palladium is the catalyst and copper is the co-catalyst. Then we saw this Johnson-Claisen rearrangement, which is the reaction of allylic alcohol with orthoester to give this gamma delta unsaturated ester. So here this reaction is catalyzed by weak acids such as propionic acids. So this is the mechanism. From this orthoester, it will this will abstract one proton, and that will undergo elimination to get this compound. Then this hydroxyl group will attack at this orthoester, followed by this hydride shift. We will get this corresponding product, and this can undergo 3,3 sigma tropic rearrangement like Claisen rearrangement to get this corresponding gamma delta unsaturated ester. So this is Johnson-Claisen rearrangement. From allylic alcohol and orthoester, we are getting gamma delta unsaturated ester. Now moving to the last lecture of the week, that was triquinane, synthesis of triquinanes by other methods. Here we have seen the total synthesis of coriolin, which is a highly oxygenated and densely functionalized triquinane sesquiterpenoid, which was reported by Venter and Correa in 10 steps, and the key steps were 4 plus 4 cycloaddition and transannular cyclization sequence. This total synthesis was reported in 1987 from starting material methyl isobutyrate, and this group could complete this total synthesis in 14 linear steps with 0.23 percentage of overall yield. Also, we discussed some more methods for the synthesis of triquinanes, which was application of Poisson-Kant reaction, vinyl cyclopropane rearrangement, aldol reaction, Nassarov cyclization, oxycop rearrangement, and then we see the total synthesis of this 4 plus 4, this coriolin by using 4 plus 4 cycloaddition. So to get the 5-membered ring, the reactions which we came across were Poisson-Kant reaction, vinyl cyclopropane rearrangement, alkylation or aldol reaction, Nassarov cyclization, and oxycop rearrangement. So we will just go through some of this. First one is Poisson-Kant reaction, which is a reaction between alkyne and alkene mediated by this carbon monoxide. From either we can use carbon monoxide gas or this uh, cobalt octacarbonyl complex as the catalyst to get the cyclopentanone ring. So this is the mechanism. So first this cobalt complex will be coordinated with this alkyne to get this kind of compound. Then it will coordinate with this alkene to get this kind of intermediate. And one CO will be inserted from this in between this alkyne and alkene, and we will be getting this cyclopentanone as the product. So alkyne insertion, alkene coordination, then alkene insertion, CO insertion, then elimination of the CO2, CO6, and insertion of carbon monoxide. So that is the Poisson-Kant reaction. Then the next rearrangement we saw was vinyl cyclopropane rearrangement or vinyl cyclopropane cyclopentene rearrangement, which is a ring expansion reaction which convert this kind of vinyl substituted cyclopropane ring into cyclopentene ring. vinyl substituted cyclopropane into cyclopropane ring. So here is the mechanism. So under photochemical condition, we can see this bond will be cleaved and we will get this radical. So this will be again undergoing homolysis so that here and here radical will be forming. Then here this double bond will form from this two radical 1 and 4, and this 2 and 5 will combine to give this cyclopentene ring. This is the mechanism of vinyl cyclopropane rearrangement. Then we saw an Asarov cyclization, that is a photochemical cyclization. From this compound we will be getting this cyclopentanone ring. This dialpha beta unsaturated ketone will be coordinated to Lewis acid. Then it will undergo this kind of rearrangement followed by this hydride shift to give this cyclopentanone. So this is a mechanism. First this oxygen will coordinate to Lewis acid, then this will attack here and this will go here, this will go here and it will form this compound. Then this hydrate will be taken, this hydrogen will be taken by the Cl minus, here double bond will be forming. Then again this HCl will be taken by this oxygen to get this enol, and which will undergo stoichiomerization to get this ketone. Cyclopentanone will be the major product. So these are the reactions for the construction of 5-membered ring. So and one more was oxycop rearrangement, which we already discussed. Like it is 3,3 sigma tropic rearrangement. So Poisson reaction, vinyl cyclopropane rearrangement, alkylation or aldol reaction, Nassau cyclization, oxycop ring closing methodology. These are the reactions which we could use in the construction of triquinanes or the construction of this cyclopentene. So now we will discuss some questions regarding the reactions which we discussed today. So the first question is, the role of copper salt as co-catalyst in the Walker process is: first, oxidation of palladium 0 by copper 2, then oxidation of palladium 0 by copper 1, then oxidation of palladium 2 by copper 1, and oxidation of palladium 2 by copper 2. So I will give some time and then you can think about the answer by that time. So as we mentioned, the mechanism of the role of copper catalyst as co-catalyst in the Walker process, it is correct option is A, the oxidation of palladium 0 by copper 2, because we are using this copper chloride. So palladium plus 2 CuCl2 giving palladium Cl2 plus 2 CuCl. That is palladium 0 is getting oxidized to palladium 2. Therefore CuCl2 is needed, and the Walker process oxidation of palladium 0 by copper 2. Now the next question is the mechanism for the formation of the molecules A and B involved respectively. Four options are given: oxidipymethane rearrangement for this first reaction and Norrish type 2 cleavage, then Norrish type 1 cleavage and oxidipymethane rearrangement, then oxidipymethane rearrangement and Norrish type 1, Norrish type 1 and Norrish type 2. So it is photochemical reaction both, but the product is different. So which will be the reaction corresponding to these products A and B? I will give some time. The mechanism for the formation of molecules A and B involved. Which two reactions are involved in this case? So here the reaction is going through this mechanism, that is first oxide methane rearrangement and then Norrish type 1 cleavage. So the correct answer is option C. And the mechanism is like this: first, under photochemical condition, this bond will be cleaving and this bond will undergo homolysis. So this both will combine to form the cyclopropane ring, and here this O dot and this carbon radical will be there. Then again this cyclopropane ring will undergo homolysis, and here will be one radical and here will be one radical. So now this will combine to give cyclopropane and this will combine to give the corresponding ketone. So as a result of oxide methane rearrangement, we will get this desired product A. Now, in the case of the second reaction, it will be undergoing cleavage at this alpha position to this carbonate. So here radical will be there, here and here also one radical will be there. Then here this will cleave to give radical here and here. Then this both will combine to give an alkene here, and this both will combine. This will combine to give a four-membered ring with this ketone here. This four-membered ring with this ketone. So that is Norrish type 1 reaction. So the first step is oxide methane rearrangement, and then this for this B, the step is Norrish type 1 cleavage. Next question is the major product formed in the following reaction. So this compound we are treating with titanium chloride, lithium aluminum hydride, and H3O plus. What will be this reaction and which will be the major product in this case? So here the reaction is McMurray coupling. So under titanium chloride and aluminum chloride condition, this will be coordinated to titanium, and here this radical will form. It will combine to give the cyclopentane ring, and then this TiO2 will be eliminated to give this alkene here. So this we have discussed. Then this under this H3O plus condition, this will be formed, that is equivalent to this one. That is here one oxygen is missing. So this is equivalent to this one. So the correct answer will be option 2. So I think now we discussed, this is the third question. 1, 2, and 3. So this is McMurray coupling. I think it's clear. And the next question is the major product formed in the following reaction sequence. So first is PPH3CHCO2ET and then heating in at 200 degrees Celsius. So which is the correct answer in these four options? So here the correct answer is first Wittig reaction is taking place. Since it is a stabilized light, E will be the major product. We will get this, which can be rewritten as this one. And then under heating condition, it will undergo 3,3 sigma-entropic rearrangement, that is Claisen rearrangement, and we will get this product. Then again, it can undergo this 3,3 cop rearrangement to give this intermediate, and here it will undergo this 1,5 hydrogen shift for the from this one, 2, 3, 4, 5, 1, 5 hydrogen shift to get this aromatized product, and then transesterification, that is cyclization, to give this corresponding lactone. We will get this as the major product. So here the correct answer will be this one, option 4. I hope it is clear. You can go through it some more time. First Wittig reaction, then 3,3 Claisen rearrangement, then 3,3 sigmatropic, but it is COP because oxygen is getting involved. Oxygen is not involved, that is COP rearrangement. Only carbons are involved in that rearrangement, but it is also 3,3 sigmatropic rearrangement like Claisen. Then 1,5 hydrogen shift so that aromaticity is regenerated, and then cyclization, that is transesterification. So this is the fourth question. Then the next question is this one. The major product of the following reaction. Treatment of this oxime with H2SO4, which will be the major product out of this four options given here. So here, this is a rearrangement reaction known as Beckmann rearrangement. It is an acid catalyzed conversion of this ketoximes to N substituted amides. So from that itself, it is clear that the correct answer is option 3. So this acid catalyzed rearrangement of ketoximes to N substituted amides, in which the alkyl group attached to the carbon migrates to the nitrogen, and the reaction takes place in the presence of Lewis acids such as PCl5 or H+. The reaction is highly stereospecific reaction, and the migration of the group is not decided by their migratory aptitude. So this is the mechanism of that reaction. That is, this OH will get protonated from this sulfuric acid. It will form this, followed by the elimination of this water molecule, and this ring will be expanded. It will go to this nitrogen atom, like it's migrating to this nitrogen atom that is given here. Alkyl group attached to the carbon migrates to the nitrogen atom, forming this imine, which can be attacked by this water molecule again, followed by the elimination of this proton to form this compound. Then this nitrogen will attack, abstract a proton from the sulfuric acid, and this will tautomerize to give this corresponding N substituted amides. So this is known as Beckmann rearrangement. It is the acid catalyzed conversion of ketoximes to N substituted nitrogen substituted amides. So this is Beckmann rearrangement, acid catalyzed conversion of ketoxime to N substituted amides. I hope it is clear. We will move to the next question. The major product formed in the following reaction. This compound, this alkene, on treatment with this aldehyde under chromium dichloride and nickel dichloride, catalytic amount in DMF RT, which will be the major product. So this is our 1, 2, 3, 4, 5, 6 questions. So with this question, we will stop our discussion for today. This will be the last question for today's discussion. So you can think about this. Which is this reaction? This is also a named reaction, and what will be happening in this reaction? So this is the reaction. Here the major product will be this one, option 4, and the reaction is this chromium first will undergo insertion at this position to give this chromium and triflate at this position. Then this bond will attack at this carbonyl carbon to give this corresponding product. So we will get option 4 as the right answer. Like here it will be chromium will be coming at this position and this will attack at this carbon. So we will get this corresponding alcohol. And this named reaction is known as Nozaki-Hiyama-Kishi reaction. So Nozaki-Hiyama-Kishi reaction is a nickel chromium coupling reaction forming an alcohol from the reaction of an aldehyde with an allyl or vinyl halide. So this with an aldehyde, the example shown below shows a chromium 2 salt solution prepared by the reaction of chromium chloride and lithium aluminum hydride to which was added benzaldehyde to form an alcohol. So this one, this will coordinate with this chromium. This here chromium will be coming, and that carbon this will be attacking to this sender, and it will convert as alcohol, and this will be eliminated. So we will get this as the product. So this reaction is known as Nozaki-Hiyama-Kishi reaction. And this is the major product formed in this reaction option 4. So we discussed 6 questions. Remaining 4 questions are there, but due to the lack of time, we will discuss it in the next class. So first question was the role of copper co-catalyst, copper salt as co-catalyst in the Walker process. So it is oxidation of palladium 0 by copper 2. Then we saw these two reactions. So then we have already seen the mechanisms for the oxide dipymethane rearrangement and Norrish type 1 cleavage. I hope this is also clear. Then we saw the mechanism for McMurray coupling and how this reaction is going on to get the desired product 2. Then we saw this like it is Wittig reaction followed by Claisen rearrangement and Kopp rearrangement, then transesterification giving this compound 4. This is the mechanism of that. Then this Beckmann rearrangement, that is this ketoximes will be converted into amides, like it is a ring expansion kind of reaction, which is acid catalyzed as well. Then in last we saw this Nozaki-Hiyama-Kishi reaction between aldehyde and allyl or vinyl halide, which is catalyzed by nickel or chromium. So That was about today's class. So I will give a brief summary of what all we discussed in today's class, and we will stop today's session. So first we discussed this week 2 assignment questions. There were a total of 10 questions. I hope this all are clear to you by now. Next week we can discuss week 3 questions also, because the due date will be over by 23rd of August. So after this 10 questions, we gave a brief summary about the lectures, 5 lectures of last week's, which was mainly trichonanes by radical cyclization, and then Wolff-Kishner reduction, Ireland Claisen rearrangement, Negishi cross-coupling reaction, then trichonanes by photochemical reaction. We saw the preparation of hydrosparish ketone, oxidipymethane rearrangement, then Suji-Trost reaction. Then in trichonanes by photochemical reaction itself, we saw McMurray coupling. Then the trichonanes by thermal metathesis, we saw this Walker oxidation and the formation of this concept of this thermal metathesis, which was formulated by Mehta's group. Then Walker oxidation, then Johnson-Claisen rearrangement, then methods for the construction of other trichonanes or five-membered rings in general, like Clopot-Syncan reaction, vinyl cyclopropene rearrangement, Nassarov cyclization. Then we discussed about 6 questions also. We met. We also gone through this reactions like oxidipymethane rearrangement, Nourish type 1 cleavage, Wittig reaction, Claisen rearrangement, Cope rearrangement, Beckman rearrangement, then this Nosaki Hiyama Kishi reaction. So I hope today's content is clear to all of you. And if you have any doubts or clarifications, you can post in the doubt session or the discussion forum in the NPTL site, or you can join the class and you can ask directly the questions. I will try to clarify all your doubts. So thank you for listening. Have a nice day. Thank you.